Well, hi everybody. I'm very happy to have with us today YLin Ma, who is faculty at the University of Michigan. So he's working on machine learning and hardware to optimize the performance and administration of database systems. So there's a lot of interest and commonality in the topics that we also know here. As we just discussed before, he has spent some time in Databricks. Before that, he graduated from CMU, working with Andy. So done very good work over there at CMU. And today we're going to hear more about Vortex. Looking forward for that. And the floor is yours.
Yeah, all right. Thank you so much for the warm introduction, Manos. Very glad to have the opportunity to visit Boston University today and to share this work with everyone. I think we'll have a roundtable later on today as well, right? So get into a more in-depth discussion. But now let me move this Zoom thing a little bit. Now, so I want to discuss a little bit of a newer work I did at Michigan. So the work is called the Vortex, essentially overcoming memory capacity limitations in GPU accelerated large-scale data analytics, right? So this work is to appear in VLDB this year, and it's already on archive. Right? We're just finishing up the camera ready and so on. But if you want, you can already find it on archive. And this in collaboration with amazing students in Michigan, each child advocate, as well as a research faculty at Michigan, my close collaborator, right? So what's the summary of today's work? So essentially, right, so if you forget all the details I'm going to talk about, so at the end of the day, right, what this work is addressed is that we observe the limited on-device memory capacity on GPUs, right? As well as the bandwidth limited PCIe links going from memory to your GPU would limit the performance of large-scale data analytics on GPUs. And so essentially, at the end of the day, that's what we observe, what we're trying to solve. So in this work, we have three components. The first is what I'm going to focus on, which is a fast data transfer primitive between CPU and GPU, right? That's what we will expand. But based on that primitive, we will also propose a programming model that is easier for you to use it, to implement, and also as well as a set of tailored query operators, right, to leverage our fast data transfer primitive as well as programming model to enhance the performance of data analytics on GPU. But for today, I'm going to focus on the first part, essentially the I/O primitive. How do we improve the speed of data transfer? The key results. So we evaluated our system or approach using the standard star schema benchmark, right, SSB, but we use a scale factor of 1,000, right? Which means that the data set size is 1,000 gigabytes or terabytes, and then the input size or the working set size of a given query is usually larger than 600 gigabytes. Right? And on the GPU we are using, the GPU has 32 gigabytes of memory. So this is far larger than the amount of available memory on the GPU. Right? And then at the start of the execution, we actually assume no memory or no data cached on the GPU memory. So all the data is on CPU memory, or could be other places, like in this case, CPU memory, and then we just stream data in onto the GPU. There's no data cached on the GPU. But then in terms of the results, we're able to achieve more than 3x performance improvement compared to a CPU-based DB baseline, which is a very fast CPU-based system. And then we're able to achieve more than 5x performance improvement over a state-of-the-art GPU-based baseline called Proteus. And then in terms of price performance, right, if we look at the per dollar throughput of our system, then it varies, but on average, it achieves more than 2x price performance improvement as well over the CPU-based database compared to the CPU solutions.
The price is $1 per throughput.
Throughput per dollar. Yeah. Yeah, and that's the summary of the results. Again, this collaboration with students as well as collaborators. So get into this work. Stop. Okay. Now, why do we want to use GPU for data workloads acceleration, database workloads acceleration? Well, GPU accelerated database is actually not really a new topic, right? It's being researched for a while, but just very briefly, right? A few reasons listed here. The first is that the GPU has a much higher computation power than CPU, especially it has massive parallel. So you have lots of data, terabytes, or even larger, then you can process it in parallel very fast on the GPU. The second is the GPU has a much higher memory bandwidth compared to CPU. Essentially, how fast you are able to access data on the memory, right? So typically, GPU has an order of magnitude higher memory bandwidth compared to equivalent CPU. And third advantage is that there's actually a fast innovation in the GPU space, especially not driven by databases, unfortunately, but driven by the newer artificial intelligence and those kind of applications, generative AI and so on. And so there are specific numbers of how much the GPU computation has increased, memory bandwidth has increased, and so on. But at the end of the day, right, the bottom line is that Moore's law has essentially stopped on CPU, but it has not stopped on GPU. So just keep being improved, especially because of the newer AI and large language model, and so on, those applications. Now, what the challenge is, right? If the GPU is so great, then why not every database vendor is already using GPU to accelerate their database application today already, right? So there are some challenges. The major observation we have is that as the GPUs, yes, indeed, they are becoming more powerful over the years, the amount of data that the database system need to process also increased significantly over the years. And that will lead to two challenges. The challenge number one, which is that the memory on the GPU, the memory capacity on the GPU is actually typically quite limited. And if you look at the state-of-the-art GPU, such as MI300 from AMD, you roughly get 200 gigabytes of memory. And then versus if you have the state-of-the-art advanced CPU-based server, you can go very easily terabytes of memory on CPU side, DRAM. And the second is that, alternatively, right, if there are also architectures like NVIDIA Grace Hopper, where essentially you just co-locate CPU and GPU on the same device. In this case, obviously, you get much higher memory capacity, and that's fun. But on the other hand, this kind of newer architecture is not widely used just yet. As meantime, it also comes with a much larger price tag. So to give this tutorial presented by Meta last year at VLDB, they are also looking to some GPU acceleration for data processing workloads. And according to them, those higher price tags would only be justifiable for the largest AI applications. This is from them, not me. And challenge number two is that, okay, so if the memory capacity on your GPU is not big enough, like 32 gigabytes or 200 or whatever, then what can you do? Well, you have to store data somewhere else. Right? And then when you need to process them, you have to send data in. Well, how does that go through? We'll go through this thing called a PCI link, which has very limited memory bandwidth. Just give you some numbers. A typical memory access bandwidth from CPU to DRAM would be around 150 gigabytes, right? Very typical. But then if you look at the widely used PCIe 4 link, right, like the bandwidth it provides from CPU to GPU would typically be 28 gigabytes single direction, or 56 gigabytes if you do bi-direction. And this is only the theoretical bandwidth. In practice, you don't even achieve that. So it's an order of magnitude smaller than what you can do to access data directly from CPU. All right. So given these two challenges, right, we think that's actually the reason why GPU acceleration for data analytics is still very limited today. Okay. Now to give you some concrete numbers on this, right? Let me show those together. Essentially here we implemented two simple operators and to do some micro benchmarking to show you some numbers. Here we have two operators, one sort and one join. And then they are both on 64 gigabytes of tables, right? Sorting is one table, join are two tables. And then the GPU we use, it only has 32 gigabytes of memory, right? So it's like a much smaller, the data does not even fit on it. So at the beginning of the operation, all the data would reside on CPU side of DRAM, right? And then we just send data in. So first we can see the graph on the left, right? You see, this like the throughput number. So the higher, the better. And then we can see that across these two operators, the sort operator, GPU actually achieved much higher throughput, compared to CPU. This is good, right? Things are getting faster. But on the other hand, on this join operator, if you implement on the GPU, especially in the case that data does not fit into GPU memory, then it actually has a smaller or lower throughput compared to CPU. And why is that? If you look at the graph on the right, that's the time breakdown on the GPU. So if you look at the sort, because sort is like it's very computation intensive. Right? You send the data in, and then you sort them, and you send them back. But in the sorting, like you have to do lots of compute. Then the time spent on the kernel computation is much higher than data transfer. Right? So most time is spent on the compute, and then GPU is very good at it, especially on large scale. On the other hand, for the join operation, because it's actually a much more I/O intensive operation in the sense that you have to first send the data in, and then you build. In this case, we use a hash join, right? And then we build the hash table. And after build the hash table does not fit on the GPU either, so I have to send it back. And then after that, I have to send the second table in, and then do the probing and so on. So you have lots of data transfer back and forth. So in this case, the data transfer time is much higher than the compute time for this operation. And the data is not even that big, right? So 2 times larger than the memory. So in that case, the GPU solution is not even faster than the CPU solution, right? That's the height of the channel. Does it making sense so far? Okay, awesome. Now, of course, like this is not like a new problem. There got to be some previous solutions. So what are the prior solutions? There are roughly two categories of solutions. In the first category, people use multiple GPUs, right? So essentially, we will say, oh, if one GPU, say you have 100 gigabytes of memory, for example, right? And then, well, what if you just use 4 GPU? You have 4 gigabytes of memory, right? Well, that is true, right? You can certainly stack things up, right? And the memory capacity just increase. But at the meantime, the challenge is that as you adding the number of GPUs on your machine, then the cost just linearly increase as well, right? So it's directly have a direct correlation. And second of all, there's also a limit on the number of GPUs you can fit on a single server. Typically, it's 4 to 8, and that's pretty much it. Of course, you can say, oh, you can scale out, you can have distributed solution, and so on. But that's just even much more costly and complicated. The second type of solution is that investigated by some other people. They will use a hybrid execution, right? CPU-GPU hybrid execution. Essentially, that's saying for GPU, memory is smaller, maybe 100 gigabytes. And then you'll have hybrid processing with the CPU, and most of the data will reside on CPU, maybe terabytes of RAM, and then the whole thing just work together, right? Which is also fun, but in many cases, the challenge still is that oftentimes the GPU is much more powerful, especially if you want to process a large amount of data in parallel. So in that case, if the system starts processing the data, and after GPU process, its local 100 gigabytes memory in a very fast fashion, after that finishes, it still needs to fetch the remaining leftover work from the CPU side, right? So at the end of the day, if your CPU is slower than your GPU, so after GPU finish processing the local work, it still needs to fetch data from the CPU to the PCIe. So it's at the end of it still the same problem, right? The utilization on the GPU in many cases is still low. And well, that's a performance reason. Another reason, which is actually not on the slide, but I want to emphasize a little bit here, is that there's also an engineering cost that you may want to consider in this kind of solution as well. In the sense that in this case, because some computations on GPU, some computation on CPU, you may split the operators to different devices, and then they are written in different language, right? This is CUDA, this is C++, you have to coordinate them, send data back and forth. The system just becomes quite complicated in that case. So comparing to either a pure CPU or pure GPU solution, the engineering cost of this solution is actually quite high. It's kind of a hybrid solution. And please, yeah.
I kind of remember reading some paper that was mentioning about the NVLink, which is much faster. So does it change the story?
Yeah, we will talk about the NVLink. Yes, actually, NVLink is part of our solution as well. But NVLink is actually not here. NVLink is here. It's between GPUs.
Okay.
So yeah, but that's part of our solutions. Any question? Okay. Now, essentially, the goal of this project is that how do we design a cost-effective yet high performance solution for GPU accelerated data analytics? Now, what do we do here? So essentially, we observe a few unique opportunities to address this challenge. So essentially, there are two facts we learn. Fact number one, there's actually evolution of GPU system in the recent years, including the NVLink I just mentioned. So initially, right, many years ago, you have this simple architecture where you have a DRAM and then connect to the CPU, a little bit higher bandwidth, and then CPU connect to one GPU, like a PCIe link, lower bandwidth. And throughout the years, you will have these multiple GPUs potentially on a single system, where the multiple GPUs, you may have multiple PCIe switches, right, that go through this GPU system. So there are 4 GPUs here, and then, for example, here there are 2 switches, and then with 2 PCIe switch, your bandwidth, your aggregated bandwidth of the system essentially double because there are 2 switches. And in many of the newer topologies, right, which, for example, which is the system that we are using for this project, you may have this architecture where there are multiple GPUs in the same server, and then every GPU would have a PCIe link connected to CPU. So in this case, even though a single PCIe link is low bandwidth, but in this case, for example, we have 4 of them, then the aggregated bandwidth across the 4 GPUs, for example, in this case, would achieve more than 100 gigabytes per second single direction, and more than 200 gigabytes bi-direction. So this is in the same magnitude of the data access bandwidth on the CPU. And that's like between CPU and GPU. And within GPUs, you will have this fast, interconnect, link, essentially in NVIDIA NVLink, or in AMD's Infinity Fabric. That is like very high bandwidth, terabytes of that. So this is very fast. So that's observation number 1, right? There's a large aggregate bandwidth from CPU to GPU on many of the neural topologies. Observation number 2, which is that many workloads running on GPUs are actually not I/O bound. Even the database workload is sending lots of data back and forth, but many workloads, I'm sure you have heard of this thing called AI and large language model and so on, right? And then, especially for the diffusion models or for LLM inference or decoding, they're actually not I/O bound. They're actually mostly compute and memory bound. So in that case, if you're running those kind of workloads, even though it takes lots of compute on the GPUs and the memory on the GPUs, there's lots of idle I/O resources we're running those workloads as well. It's not true for every workload. If you're running training distributed, by distributed, I mean multiple GPU training, it requires lots of memory bandwidth back and forth as well, right? But for inference, deep learning, and so on, they don't require as much I/O. So yeah. So what our solution, essentially that's what I'm alluding here. Right? Essentially, we think there's actually an opportunity to co-locate different types of workloads, so like in a multi-tenancy scenario, so that we can redistribute the resources in a multiple GPU systems to different workloads, so that they complement each other. So that's essentially the opportunity we're trying to leverage. Right? So just to set the stage, right? So to be clear, what our target system or example system, this is a system we used in our evaluation and so on. So we are targeting a single multi-GPU server, right? And then on each GPU, we have a single CPU socket connected to 4 GPUs via the PCIe link. Every GPU will have PCIe link. And then within the GPUs, we will have a fast inter-GPU communication via either AMD Infinity Fabric or NVIDIA NVLink. Right? That's the topology we are targeting. Now, our target workloads, essentially, we are targeting the workloads where we want to optimize the database workloads, right? We want to make them faster. But then in the background, we are assuming there could be some disjoint AI models running behind the scene. And then there could be models that they are not using lots of IOs on the GPU, but using lots of compute. And then for now, we are assuming more like a multi-tenancy setting where they're just completely independent workloads. However, there are also emerging workloads these days that even for a single workload or the same customer, you may actually have database workloads and AI workloads running together. For example, there's this neural thing called the retrieval augmented generation, and you've heard of it. So essentially, yeah, you may have a big, large data sets and then lots of data. You want to retrieve some documents. Maybe in this case, could be some documents back to the database. And after you retrieve the data from the database, you send that to LLM and doing some text generation and so on, right? So this could be the case in the case that just a vector database, or there could be a variant of this RAG pipeline where you have some traditional database, large data set. You do some SQL analytics and perform some queries. Like natural language to SQL is also a very popular topic these days. And after that, you execute your SQL query on the relational database. Again, you send that to an LLM to organize the answer and give you a text response. There are those kind of workloads, emerging workloads these days that may have database as well as AI on the same server. But that's not what we are focusing on in this work just yet. Right? So we are more focusing on disjoint setting. Right? So what is our solution? Right? So essentially, right, at high level, Vortex is trying to alleviate the I/O bottleneck in GPU accelerated analytics by resource distribution on the GPUs. So it has, 3 components, right? Which, what I'm focusing on is the first one, but, a kind of 3 components. The first is the improved I/O transfer primitives, right? Leveraging the observation we just had. And the second is a programming model, just make it easier for you to implement things. And last component is some execution operators, right? Leveraging those techniques. And then I'm focusing on this particular component. And again, just to clarify things, in this setting, we are assuming that we have 4 GPUs and 1 particular GPU. We are using it for data analytics, SQL essentially. And we think that's actually already very powerful. It's like powerful enough. And then in the background, we have 3 GPU servers that are doing some AI inference work, right? They are very compute intensive. They'll use lots of memory on those GPUs, but not so much I/O. And then, what exactly is the solution, right? Essentially, the solution is a SDMA-based high-performance I/O primitive. So SDMA just means System Direct Memory Access. Essentially, is the API you use on GPU to transfer data. And the goal here is to transfer the data from the CPU side of DRAM, which typically has much larger capacity, to GPU 0, which is our targeted GPU, as fast as possible. Right? That's the goal. And what's the baseline? Well, the baseline obviously is that GPU 0 has its own PCIe link to the CPU, so it just just use that to transfer. And of course, the drawback is that if other GPUs have a little bit of idle I/O resource, that you may not be using the computer. And then our approach, Vortex, right, very high level, very straightforward, which is that we are proposing to use all CPU, GPU, PCIe links, as well as the inter-GPU infinity fabric to route data through other GPUs to GPU 0. Right? This is our solution. So essentially, on GPU 0, it's still direct transfer, and on the other GPUs, we have a small amount of buffer. Doesn't need to be very big, right? Small amount of buffer allocated for each of these GPUs, and then used as a forwarding GPU to get data to GPUs. Of course, right? This is only effective when GPU 1, 2, 3 are not running I/O bound, such as AI inference, so that their SDMA path is underutilized. Now, this all sounds very, very straightforward, right? It's like if you just send multiple requests through the GPUs, you hope this would just work as that, right? Unfortunately, it's not that straightforward. So essentially, if you really just directly submit concurrent data transfer requests through these GPUs using their native APIs, such as the streams or events APIs available on both CUDA and HIP, right? So if you just using the hardware native APIs submit this concurrent data transfer request, the performance is actually not very satisfactory. We try that, we measure it, the performance is actually not quite good. And why is that, right? What are the challenges? So essentially, we observe 2 challenges in this setup, right? They're all related to hardware limitation. The first is that there's this head-of-line blocking problem exists in many GPUs. So essentially, in GPUs, right, in many cases, when you submit concurrent requests through multiple streams, even though at a software level, they are independent, right? They don't block each other. However, the multiple software like data transfer request streams will traverse many layers of software queues. At the end of the day, they may end up in a limited set of hardware management queues. So eventually, even though at a logical level, your data transfer are not blocking each other, just completely, at a hardware level, they're actually blocking each other. So it's very difficult to achieve a good performance or stable performance. So usually this is called a head-of-line blocking. It's actually a well-documented phenomenon in many NVIDIA or AMD GPUs. The second challenge is that when we do this like a concurrent data transfer through many GPUs, that actually puts lots of data transfer request pressure on the CPU side memory controller. Right? So essentially, this combined bandwidth of activating all the PCIe links altogether simultaneously that exceeds the CPU side memory controller bandwidth or capacity, that will lead to a very, again, unstable and non-uniform bandwidth availability across different paths. So you don't have to look at the details here, but essentially we have 4 GPUs, 0, 1, 2, 3, right? And then we have different scenarios, different type of transfer and so on. And then this is the bandwidth we measured. Just across different scenarios, look at different GPUs, you just get random, data transfer speed, right? Very unstable. So which is not good either. So now, what is our solution? Well, essentially, our solution is essentially bypass the hardware queues and scheduling and so on. Essentially, we implement a customized or software data transfer scheduler essentially, right? And then we manage all the package data transfers and so on by ourselves at the software level. Essentially, that's what we are doing. Before I walk through the solution, just again some terminologies, right? Here we have 4 GPUs, CPU there, GPU, yeah, 4 GPUs here, and then we want to transfer the data between CPU and GPU 0, which is our target GPU, and we use the term H2D to refer to host to device data transfer, right? So essentially, CPU is a host and GPU is the device, right? H2D, host to device, and D2H is device to host data transfer. It's like because in many cases you have to send data back. So sending data from GPU back to CPU, D2H. Now, what's our solution? So essentially, again, it's like a software, package, right? Yeah. So essentially, yeah, we propose a software solution to this, and we have a software scheduler built for this. So we have essentially a few components for this, piece of software. The first is a global scheduler, right? So it's a software live on the CPU side to ensure, balanced and high performance, load distribution. And then on every GPU here, we have 2 link workers, right? That is managing the data transfer on both directions, both D2H and H2D. And also on every GPUs, we'll have 2 memory buffers. Right? We will cache essentially the packets, or it's a buffer for the packets on each GPU for the pipeline data transfer. And again, the buffer is not that big, right? In actuality, in our experiments, we use 80 megabytes. That's usually 2.5% of the available memory, on the GPU. Okay. And now, so we'll walk through this example how this software package works. Like it's also not that complicated. Essentially, at stage 0, the data all resides on the CPU side of memory, right? And again, there's no data caching on the GPU side of memory before the execution starts. That's the setup that we are looking at. And then in the first stage, we will essentially packetize all the data, right? To split all data into small packets, and then populate all the packets to the H2D queue in the global scheduler. And of course, we'll also initialize all the link workers on the GPU. And here, when I say populate, there's no data movement, right? We just literally, we look at all the pointers of all those data in memory, and we send all the pointers to the queue. And there's no data movement so far, but we populate them into the queue. And in the next step, we'll essentially activate all the links to pop the data from the global scheduler queues to the buffered memory space on each GPU. So this is actually data movement. This is PCIe link. And then for GPU 0, you just directly put that, transfer that into the targeted GPU. For other rest of GPUs, you put them into the relevant buffers. And
so you also have buffers, same buffers in GPU 0? Like these H2D buffers, because you saw them there. Do you need them in GPU 0 as well? It's a small amount of memory.
Yeah, I think you might not. I forgot the details,
okay.
But I think you might not. Yeah. Yes. Okay. In the last step, right, essentially, all straightforward, you just essentially push all the buffer data from GPU 1 to 3 to GPU 0 through the high bandwidth interconnect between the GPUs. Yeah, it's like you're only using a small portion of that bandwidth. Okay. So, well, essentially, yeah, you'll do this in a pipeline fashion, right? Essentially, CPU and the GPU just keep pushing data packets back and forth in these 2 queues, and then the GPUs just keep popping packets from global schedulers as well. So essentially, when I say pipelines, mean that when, for example, in this step, when, for example, a forwarded GPU push data from here to here, you can actually grab the next, packet from CPU to GPU, right? So you can take a pipeline fashion. That's what I mean. All right. What the benefit of this approach? Well, essentially, it's improved data transfer speeds by using all the available links in the system. And also, essentially, in this design, we let the link workers only pop packets from the global scheduler on PCIe links when the bandwidth become available. Essentially, this way, we can bypass the height-of-line blocking problem. We also have a adaptive flow control policy that we dynamically, essentially schedule the packets in both directions to get a balanced data transfer in both directions. So this will address the non-uniform bandwidth problem. So
does this mean that maybe at some point one CPU will not forward the packet block or whatever because it's busy with something? Right?
Yeah, exactly. Oh, it's because it's slow.
Or because it's slow.
Yeah, exactly. Because the bandwidth is just imbalanced.
Right.
Yeah. And the limitations, all opportunities for future work, essentially a few things, right? First, obviously, but I will show some numbers, right? But this will actually still cause a little bit of a slowdown in the backbone AI applications running on the forwarding GPUs. Right? So we'll have some details later. But to give you a heads up, generally it's below 10%, but in some cases a little bit over 10%. So yeah. And then it could also have some security privacy implications. You have multi-tenancy, using links from other people, a little bit of that, which is actually not my area of expertise, but there could be some implications. And also the third one is more of an implementation thing in the sense that currently we only implement one destination GPU and 3 forwarding GPU. You can have other combinations, right? But it's just just what we implemented so far. Now, you have an idea of why the
question. So does the head of line blocking, the fact that it's gone now, I guess, does this imply that your workload has like the order of packets is independent from one another? In other words, like GPU 0 can ingest any packet, but it doesn't matter the order in which the packets come.
Yeah, it doesn't matter, right? But even though it doesn't matter in our workload, but head of line blocking means that even though it doesn't matter, at hardware level, they may still block each other.
Right, but does your solution then though have issues if like the workload that I have has like an order causal relationship between like the packets that are incoming?
That's what I say again.
Like, does this solution have issues then if like my workload has a reliance on like the order of packets that are coming in?
You may need to customize those. So in our implementation, or for the operators we implemented, we never had that scenario. But yeah, if you have, you may have to have some customized logic, right? Essentially to block things, to coordinate things by yourself, essentially. But in that case, the hardware won't solve that for you either, right? Essentially, in hardware, head of line blocking means that at the software level, there's no logical relationship.
Yeah.
At the end.
Okay. Thanks. Yeah.
So okay, so what's the benefit of this like a software package? So essentially, here in this case, we have the y-axis as the throughput we measured for data transfer, right? The higher the better. And the x-axis is like a different type of scenario. Essentially, how much you are doing H2D, how much you doing D2H, and so on, right? Different scenarios. And then on this upper line here, that's the theoretical upper bound. Essentially, that's from the hardware spec. If you assume an optimal case, look at the hardware spec, how much maximum I/O bandwidth you can achieve in different scenarios. And then this black line, essentially that's the hardware API, right? So you submit directly to the event streams and so on. Naively using the hardware API, that's the throughput you get. You can see sometimes it's good, sometimes it's actually good, sometimes it's pretty bad, not stable and so on. And then all these lines in the middle is our approaches with different data transfer granularities. You can see the throughput is much more stable, and generally speaking, is pretty good. Right? Okay. Now, there are a little bit more details which I won't get into today. Right? Essentially, the programming model, execution, and so on. Oh, lastly, just to emphasize a little bit. So our approach is optimized for throughput. Right? But then it's using the SDMA engine, which means it's asynchronous. So it actually has a little bit higher latency to activate. If in some cases you just want to access a tiny bit amount of data, right, some kilobytes, 100 kilobytes or whatever, right, then you will use a combination of different approach called a zero copy. You can directly access the DRAM, on the CPU side from a GPU using this approach, which is very low latency but a very low bandwidth as well. So you have to balance them a little bit. Now, into the final evaluation, right? Essentially, we have 2 types of experiments. The first we call it interference-free, but essentially we have GPU 0 running data analytic workload. GPU 1 to 3 are completely idle. Right? You don't see in an ideal case by using all the PCI links for the throughput. The second is called interference analysis, which has the GPU is running data analytics, and GPU 1 to 3 they are running some AI workloads at full capacity. Right? But if they are like some diffusion model, text embedding, and so on. Essentially, they are not like IO per se. Right? And then we have the buffer size of 80 megabytes on each of the forwarding GPUs in all the experiments, right? Essentially, we have for each, forwarding GPU, we have two buffers, right? D2H and H2D. And then for each buffer, we actually have to have two slots, right, because of the pipeline. But in total, every GPU has 80 megabytes.
Or should like 20 per buffer or something?
Yes, exactly. So yeah, it's like AMD, some HPC cluster, and then yeah, it's like so in terms of the GPU, we have four MI100 GPU connected with the AMD 7-way 13 CPU, and this GPU is actually not super high end. It's like a fairly moderate GPU, but we already achieved pretty good performance with it. And then on device memory, and it's like 32 gigabytes, right, which is far less than the input workload size. And this GPU, the CPU is also pretty good, right? It's a fairly decent server grade CPU. Okay, so again, like a star sigma benchmark, average across 13 queries, no data cached on the GPU to begin with. Okay, here are the results. So essentially here, we normalize the DuckDB CPU baseline to 1 speed, right? So the higher, the faster the system is, but DuckDB is 1. And then we can see first the first Proteus GPU baseline essentially is a GPU-only solution offered by Proteus. In this case, it's much slower than the CPU because data does not fit there, right? It actually does not fit there at all. It's much larger. So you have to send all the data in very slow. And Proteus actually also offers a hybrid solution, use some CPU, some GPU. But in that case, you still have to do the coordination, right? And after the GPU finished processing, you still have to grab data from the CPU and so on, right? So not very fast either. Oh, by the way, all these solutions, they only use one PCI link, right? Let's just make it clear. Right? And also a naive solution, essentially it's the same software as Vortex, but only using one PCI link. Everything else, it's the same software, except it's using one PCI link and doesn't have the optimization that balance between zero copy as well as SDMA. It doesn't have that either. But other than that, it's the same software. And yeah, if you use only one PCI link, it doesn't work very well either. But now with Vortex, right, if using the I/O of all the PCI links, as well as essentially that's the biggest advantage. It can achieve much better performance compared to other solutions. Right? So essentially I/O is not a bottleneck anymore. And another thing interesting to observe here is that for all the other solutions, none of them is faster than CPU. Right? So if your data is much larger than the available GPU size, and if you cannot send the data to the GPU fast enough, none of them is faster than CPU.
So in terms of the CPU execution, is this it's multi-thread? Right?
Yeah.
And what is how many cores does this CPU have?
Oh, it's a lot. It's 80 cores, something like that. Well, it's not may not be exact, but something like that. Yes. Essentially the observations that proposed I/O primitive significantly speed up the end-to-end OLAP curves. Now, in terms of the interference analysis, right? So how does the impact? So here we are running the AI applications in the background, right? And we have different applications, some stable diffusion models, some embedding models, some Llama decoders, prefill decoder, or something like that. And then we have different database workload patterns, right? With different data transfer ratios. It's really maybe sort or join operator. You have like a fairly balanced mix of H2D and D2H. Or you have, for many of the SSB queries, you have a predominantly H2D data transfer, or in some other workloads, you may have predominantly D2H, which is not that common, but we manage it anyway. You can see at a high level, right, there's like a slowdown of various AI workloads running in the background. And then generally speaking, for most cases, it's less than 10%, right? In some cases, it's higher. But here, if you look at the first row, right, here, we have a mix of data transfer, patterns. Then it's generally a higher impact compared to the other two scenarios, right? So essentially, if you have a mix of bidirectional I/O traffic, it will put more stress on the computer resources on the forwarding GPUs, so a little bit higher impact versus you only have one direction. Right? That's one thing. Another thing is that if you look at the columns at the back, right, like for the Llama 3 or decoders, different batch sizes, then it also has a higher impact as well. And why is that? Well, because for those AI workloads, right, specific AI workloads, they are more memory intensive in a sense that they use higher memory bandwidth. Not by memory intensive, I don't mean they use more memory on the GPU. I actually mean because the data, the workload fit on GPU anyway, right? So the workload will be long. But then by memory intensive, I actually mean these two types of applications require lots of memory bandwidth on the GPU, which we also, we have to take away a little bit, right? So in this case, because they are more memory intensive workloads, they will experience a greater slowdown due to the competing memory bandwidth resources. That's usually the operation. Well, that's pretty much all the results, right? There are some open questions. I'm sure if you have some comments, I'm also welcome. But essentially, some open questions we can think about. For example, how do we reduce the performance impact on the AI or other workloads running on the forwarding GPUs? Right? Or how do we position this technology if you have virtualized GPUs? You can do everything. Or how to use these primitives for maybe potentially other emerging data AI workloads, right? Or is it possible? Because now we have resuming multi-tenancy, right? But if you don't have multi-tenancy, if it's just data analytics workloads, is it possible to still achieve high GPU utilization? But maybe you run different types of queries together, right? Queries with different characteristics, you balance them a little bit. And lastly, what should be the correct processing model for out-of-core GPU queries? By out-of-core just mean data larger than GPU memory. Do you send them back and forth? Do you fuse all of it together? Things like that. All right, so just to wrap things up, essentially in this work, we observed that GPU accelerated data analytics have been facing the challenge of limited GPU memory size and PCIe bandwidth. So in this work, we proposed a resource redistribution and workload co-location idea using multiple GPUs, which significantly alleviate such limitations. And we think there are many opportunities to leverage this idea for many of the data processing and all AI workloads. And yeah, that's pretty much. Looking forward to any comments, discussions, or even maybe interest to collaboration with everyone. Thank you.
Any more questions?
Good work. But I was curious if you guys have taken a look and factored in that GPU Direct. Yeah.
So that's a good point, right? GPU Direct, I think, can potentially alleviate this issue as well. So actually, I think they complement each other, right? So I don't think they are necessarily an exclusive solution. So yeah, I think it can help. On the other hand, GPU Direct is not available on all devices either, right?
Right.
Especially if you rent a machine in Azure or AWS, oftentimes they don't have GPU Direct. So.
What is the bandwidth of the mirror copy data transfer? And how you said you kind of needs the usage of the transfer.
Yeah. Obviously, I forgot, but it's like a much lower. It's like at least an order of magnitude smaller.
And how do you leverage when to use the zero copy and?
It's really not that complex. Essentially, it's an equation. Right? You do some calculation based on the throughput numbers and so on, define a threshold, and then if you're larger than the threshold, you use SDMA, smaller than threshold, you use zero copy. But in that case, you also explain. We have a section in the paper as well. You could read, but in some cases, you also have to estimate how much data you may fetch as well, based on kinetic and so on. So, do some little estimates.
That means you have some. You at least need some accurate estimation before you digest the data. For example, if we have some complicated filter condition and data, we may have incorrect estimation because when we scan the data from the memory, we may already can skip many days.
But in that case, I mean, estimate, first, I see your point, but I think by estimate, actually don't mean kinetic estimation because, well, what you said could be an approach, but in this case, we actually assume all the computation happens on the GPU. So even for the filters, we send the data in and then do it on the GPU. Yeah. But after that, but you may have multiple filters. After the first filter, you will know how many tuple left. Right? So after you finish the filter, you may know how many tuple left. Then at some point, data may become very small. And at that point, you will know.
So by the way, the system you are using for the GPU processing, is it based on Proteus that you mentioned, like the Vortex experiments?
No, it's not based on Proteus. Proteus is a bit complicated. The code base to use is based on Crystal. If you know the Crystal, it's from Wisconsin.
Okay.
It's like a much simpler library that we can install.
Okay.
It's really just a set of operators, and you manually stitch them together.
Okay, yeah, I understand.
Yeah.
I was curious about the implementation that you use for the GPU.
Yeah.
That makes sense.
Yeah.
One quick question, I might have missed this, but you know how you showed in your example that, let's say, there was GPU 0 and then there was 1 to 3, and then the forwarding was happening from 1 to 3 and it was going to 0, right?
Yes,
GPU
yes.
0. So is there a case where you would have to switch it and now forwarding has to happen to GPU 1? Right? Is there such situation?
Yeah, in this case, we didn't. We just assume 1, 2, 3 is all for forwarding. They're always dedicated to AI, and 0 always dedicated for database. But there's no reason you couldn't do that. It's just in this experiment, in our current implementation, we just assume one particular GPU dedicated for data analytics, and that's the target destination.
So you said something about this unpredictability of the bandwidth between the that you have this heat map over there. So the unpredictability, just to understand this a bit better, was it that it might happen that at some point any link between 2 to 0 would be slower than the one between 1 to 0?
No. It's not the. I mean, it's the PCIe.
Oh, the PCIe.
Yeah, we observe. It's a pressure on the CPU memory controller. So the PCIe might be.
Okay. I see. That makes sense.
Yeah.
Anything else? All right. The second speaker again.